Hi. Hi. Welcome. Yeah, once again, this is part 15 in our exploration of Lagrange's theorem. Lagrange's theorem. Right. So this is part 15 of our exploration of this theorem, and we've come to we've learned quite a lot so far. For instance, while Lagrange's theorem is telling us if G is finite, then we know that for any subgroup H of G, the order of H has to divide the order of G. Right? This is one of the things. Isn't this one of the things we concluded? Uh, did we also say that if G is finite, then for all G element of G, the order of little g must divide the order of the group? What did we conclude when we said that if, let's say, the order of a group equals to some prime? Did we say that this implies that G is cyclic group, and furthermore that every non-identity element of G is actually a generator of the group? That is, for all G element of G and G not equal to the identity, if the order of the group is really prime, then the group G can be generated by the element little g, right? So let's see. What else? What else were we able to say? Just recently in the previous video, did we come to the conclusion that if the order of a group is p to the alpha, where p is a prime and alpha is greater than or equal to 1, then that implies that there must exist some subgroup h of g such that order of h equals to p, right? So this is the result we seem to have come to recently, right? So normally when we have a result, we want to think about, well, what's the use of it, right? So okay, so fine. If it's indeed true that for every group of order p to the alpha, there is a subgroup of order p, well, why is that useful information, right? So one possible use is, perhaps let's think about this. Let's say we have a problem and we've been given some group, let's say, I don't know, we've been given some group M. M is some group, and we're wondering whether M has a, let's say, we're wondering if M has a subgroup of prime order, right? Let's say we're confused about whether M has a subgroup of prime order or not. Well, given what we now know, is there a strategy we can use a potential strategy to show that, let's say, a certain group M has a subgroup of prime order, right? How about, suppose we had the M and weren't sure, we're wondering whether does there exist some subgroup of order of M, does there exist some L? That's the question. Does there exist some L subgroup M such that order of L equals to some prime P, right? Let's say we're wondering if this is true or not. Well, what now, given what we know, can you think of a strategy that we can use to figure out if a given group has a subgroup of prime order? Right. Suppose we're able to show that the order of M equals to some prime P raised to the alpha. Right. Can we use this information and our knowledge of this previous theorem to conclude that, look, there must be some subgroup of prime order? Right. What are the uses, though? So given this, could you come up with a use of the theorem? For instance, if we said the following, if we said that one of the uses of this theorem, that a group of order p to the alpha always has a subgroup of order p, could we say that one use of the theorem is to help us guarantee whether or not a given group has a subgroup of order p? Right? Could that be one use of it? How about, can you think of another use of this theorem? What else can we do with it? Well, one thing is, we have a lot of cyclic groups out there. For instance, uh, think about the group, well, just the group Z, right? The group of integers under addition, right? Would you agree that this group can be generated by the identity element? That is, if you added 1 to itself a couple of times, or maybe you added the inverse of 1 to itself a couple of times, would you be able to generate any integer? Right. Right. So, is it true that z plus can be generated by the element 1? The element 1. That is, if you had some integer n, can you think of it as either a sum of ones, or as, if it's a negative number, perhaps as a sum of negative ones? Right? Because in this case we're saying, well, so maybe this might be a little tricky. So what do you think 1 squared is going to be for the group z plus? Will it be 1 plus 1? Okay. What about 1 cubed? What would that be? 1 plus 1 plus 1? So given this information, right, what about maybe the inverse? What's 1 to the negative 2? What do you think that's going to be? Right. Is it going to be equal to 1 inverse to the 2? But what's 1 inverse? Isn't 1 inverse negative 1? So we're saying that 1 to the negative 2 is the same as negative 1 to the 2. But what's negative 1 to the 2? Isn't negative 1 to the 2 the same as negative 1 plus negative 1? Right. So when we talk about the set of all 1 to the n such that n is an integer, such that n is an integer, right? Are we still talking about the set of integers here? Right. Here with 1 to the n is just being defined to be 1 plus 1 plus 1 plus 1 n times, right? So here we have ourselves a cyclic group generated by the identity element, right? So, however, notice that while 1 is the generator, we can ask the question, is there any other element that's a generator? For instance, does 2 generate the set of integers under addition? Right? That is, if we considered all 2 to the n, where n is an integer, will we be able to get the entire set of integers back? Right? What would this give us, 2 to the n? Right? Where 2 to the n is being defined as 2 plus 2 plus 2 n times, right? Or if it's a negative, it's going to be negative 2 plus negative 2 plus negative 2 plus negative 2. So the question becomes, are there certain integers that will never be obtained by adding a bunch of 2's or a bunch of negative 2's? Right. Right. Namely, what integer? For instance, maybe another way to think about the question is, can you think of an integer which we can never generate by adding up a bunch of 2's? How about 3? Is there any way you can get 3 by adding up a bunch of 2's and negative 2's? Alright? So if that is true, then how can 2 generate the entire set of integers? If we can't find 3 by adding up a bunch of 2's or negative 2's, how can the set generated by the 2's, by sums of 2's, how can 2 generate the entire set of integers is the question, right? So here we're noticing something interesting. Sure, we have a cyclic group. The set of integers is a cyclic group. The set of integers is cyclic. That is, the set of integers can be generated by the identity element. Sorry, not the identity element, but by 1. It's not the identity under addition is what? Isn't that 0? Okay. So the set of integers under addition can be generated by the number 1. But not every integer is a generator. For instance, we're seeing that 2 is not necessarily going to generate the set of integers. 3 may not generate the entire set of integers. That's potentially possible, actually, isn't it? Actually, it is true, right? So, right. Please see if this makes sense to you. So, just because a group is cyclic doesn't mean that everything is a generator. Right? Right. And in particular, can the identity element ever be a generator? If our group G, if the order of our group G is greater than 1, that is, if it's not the identity element, and let's say that it's cyclic, can the identity ever generate the group? Right, is the question. Well, what's the identity? Isn't the identity 1? Right. What's 1 raised to any power n, where 1 is the identity? Isn't that just 1? Okay. So if a group has more than one element, let's say the group has elements 1 and G1, or something like that, some cyclic group, right? How can 1 ever generate the group? How can multiplying 1 by itself a bunch of times ever give us anything other than 1? Right, is the question. So are we saying that are we saying that, okay, we're saying that, look, if the group is, right, we're noticing something bizarre here. Like, if the order of the group is not the identity, if the group is more than the identity element, then we're noticing that maybe the identity element is not going to give us the entire group. It's not going to generate the entire group. But the question is, okay, fine. What if we have a group that is greater than 1? Right? That is, if we have a group whose order is greater than 1, right? And let's suppose that G is cyclic. That is, G is some cyclic group, right? Can we ever find, or maybe another way, a better way to phrase the question is, can we ever find a cyclic group which is such that it is generated by every non-identity element generates it, right? So, I mean, one of the obvious ones we had was, well, I mean, just any group of prime order, right? If order of G equals to a prime, right, then let's say we take some G element of G such that the element G is not the identity element, right? All right, the order of the G is a non-identity element. Well, what does Lagrange's theorem tell us? Doesn't it tell us that the order of G must divide P? But if the order of G divides P, what does that tell us? If G is not the identity element, what order must G have? Isn't the order, can we say that the order of G equals to P? Okay. If the order of G equals to P, what are we saying? Isn't G to the 0, G to the 1, all the way up till G to the P minus 1, isn't this thing just equal to the group itself? Right. So what are we saying here? Are we saying that G can be generated by any non-identity element, little g? Right. Okay. So if a group has prime order, are we saying that every non-identity element generates the group? Right. So okay, fine, that's all well and good, but what does it have to do with our previous theorem here? Because we've been thinking about applications of our theorem that if a group has order p to the alpha, then there must exist a subgroup of order p. Right. So what potential uses could it have? Well, what if we have some group M and we're wondering whether, and we have the following question, say, does the group M have a cyclic subgroup, right? Does it have a cyclic subgroup whose every non-identity element is a generator? Right. Right. So this is kind of convoluted. Suppose we have a group M. We're wondering, is there some subgroup, let's say K of M, which is cyclic, such that K is cyclic, and every non-identity element of K is a generator for the cyclic group. That is, for all little k in K, such that K does not equal to the identity, little k generates the group K, right? If we have a group M, how can we ever decide whether there is actually a subgroup K of the group M, and that the subgroup K, big K, can be generated by every non-identity element, right? The cyclic subgroup K can be generated by any non-identity element. What would we need to show in order to guarantee that this is true, that such a cyclic subgroup whose every non-identity element is a generator exists? How can we show that if all we have is M? Right? Can you see how our theorem might enable us to conclude this result? Right. Suppose we showed that, well, okay, our group M actually has order p to the alpha for some alpha. What would that tell us? Wouldn't that mean that there exists some subgroup K of M such that order of K equals to a prime P? But if a subgroup K has prime order, doesn't that mean that every non-identity element is a generator of the group K? That is, doesn't it mean that for all little k element of K such that K does not equal to 1, doesn't little k generate k? In fact, if order of k equals to prime, isn't k cyclic? Right? So maybe, can you think of any other uses? Are there any other uses of knowing that, look, if a group has order p to the alpha, then there must exist some subgroup of order p? Right? What other value could that have for us? Right? Maybe another basic question to ask is, well, what about the converse? Right? What about the converse of this theorem? Is it true that if a group has a subgroup of order p, does that mean that the group is of the form p to the alpha? Well, what's the converse of this going to be? So here's the question. Here's the question. Do we have some space? All right, right. Let's make space to the right. So now here's the question we're being asked here. Well, suppose, okay, so here's it's going to go. Let G be a group, right? G is a group. Suppose that there exists H subgroup of G. That is, there exists H subgroup of G, right? Suppose there exists H subgroup of G such that order of H equals to some prime. Well, does that this imply that order of G equals to p to the alpha, right, for some alpha greater than or equal to 1? Is that necessarily true? Right? That is, if we have a group and it has a subgroup of order p, does that mean that the order of G of the group itself must be a prime power? Right? Do you think this statement is true, the converse? Okay, how could we decide whether or not the statement is true? Right? Well, maybe could we find a counter example? Right? Would that work? So let's pick an example. Like let's think about the group Z mod. No, probably have some simple group. How about Z mod 6Z? Okay. Here's Z mod 6Z. All right. Question. Well, what are the elements of Z mod 6Z? Is there a 0? Is there a 1? Is 2 an element? What about 3? Is 4 an element? What about 5? All right. Is this Z mod 6Z under addition? All right. So let's see. Well, let's call this G. Let's call this group G. All right. What's the order of G? How many elements are in the group G? Are there 6 of them? All right. Well, can we find some subgroup of prime order? Well, can you think of, for instance, is there any element here of order 2? Right. So what's 3 plus 3? Isn't that 6? But what's 6 mod 6? Isn't that 0? Okay. So is the order of 3 equals to 2? So let's consider this set then. How about H? What if we set H equal to 0 and 3? Right? Well, first of all, is H a group? Right, let's check that. Because, I mean, one thing we notice is if H actually turns out to be a group, let's suppose it is actually a group, then isn't H a subgroup of G? Right? And what's the order of H? Isn't the order of H 2? Okay. If the order of H is 2, well, isn't 2 a prime? Right. But what's the order of the group itself? 6. Right. So, is 6 a prime power? Isn't 6 just 2 times 3? Right. So, I mean, would you agree that order of G equals to 6 is not equal to p to the alpha, where p is some prime and alpha is some integer greater than or equal to 1? So, if we found an example of a subgroup of prime order, if we found an example of a subgroup, if we found an example of a group G whose subgroup H is of prime order, but the group G is not, but the order of G is not a prime power, right? How can it be true that just because you have a subgroup of order P, you must also have that the group itself has order P to the alpha, right? So can this statement be true? Can this claim that if there is some subgroup of G whose order is P, then order of G equals to P to the alpha? Can that statement be true given that we found some G which is Z mod 6Z, we found some H which we're saying which at the moment we're not sure if it's a subgroup, but if H actually turned out to be a subgroup, could the converse of the theorem we've been trying to prove possibly be true, right? So what are we saying here? Well, I mean, first we need to check, is H a subgroup of G? That's the question. If G equals to Z mod 6Z, is H a subgroup of G? What do you think? Right. Please see if you can figure this out. Well, if H is a subgroup of G, well, haven't we just found a counterexample to this supposed claim that having a subgroup of order P guarantees that the group has order P to the alpha, right? Right. So perhaps the converse is not true, perhaps, right? But again, it's up to you to determine whether or not that's the case. So what else is there now? What else can we investigate here? How about this claim? Would you agree with this claim that suppose that the order of G equals to P to the alpha? Does this imply that there exists some element of the group G such that order of G equals to P? Right. Before it looks similar, but it's slightly different, right? Before we're saying, look, if we have a group of order P to the alpha, then we have a subgroup of order P. But is it also true for elements? If we have a group of order P to the alpha, does it mean that we have an element of order P? Right. Is there any way the theorem we proved before could help us to solve this problem? Right. Or in what ways could we establish if this is true? Right. Well, for now, let's see if our previous theorem can help us, right? So since we are, after all, we're trying to see if what the consequences of our theorem are. Well, suppose that the order of G equals to P to the alpha, right? Doesn't that mean that there exists some subgroup H of G such that order of H equals to P? Okay. But if order of H equals to P, doesn't that mean that H is cyclic? Doesn't it also mean that for all little h in H, where H does not equal to 1, aren't we saying that any non-identity element of H is going to generate the group H? If every non-identity element generates a group H, aren't we saying that the order of any non-identity element H equals to the order of the group itself? But what's the order of the group? Isn't the order of the group P? Okay. But if H is an element of H, and H is a subgroup of G, isn't H an element of G as well? If H is an element of G, then haven't we found some little g in G, namely H, such that order of G equals to P? Right. So can we conclude then that so long as we have a group of prime order, we also are guaranteed an element, so long as we have a group whose order is a prime power, can we conclude from there that we are guaranteed to have an element whose order is the prime itself? Right. So does this theorem follow as well? I think it has a name. The name may be Cauchy or something like this. Either it's Cauchy's theorem or possibly Cauchy, but not sure. Yeah, anyways, the names are not as important as the ideas themselves. So at least we are getting somewhere. We're learning a few ideas here. Is there anything else? Anything else that this theorem could be telling us? The fact that there's always a subgroup of order P to the alpha? I mean that if there's a group of order p to the alpha, then it must have a subgroup of order p. Of what other value could that be to us? All right. At the moment we're blank. We have no idea. So yeah, we're gonna end this video here. Thank you very much for watching this video, and have a relentless week. Bye.